we start Module 2, Part B, Asymptotic Notations. B.1, Introduction to Asymptotic Notations. This part, it is very abstract. So, because in order to do the analysis in some efficient way, so we have to do something very abstract. All right, so first, let me start with this problem. Limits of two growth functions. We need to find, when we compare two growth functions, which one grows faster, which one grows relatively slower. One important way to do it is find the limit of the ratio of two growth functions when the problem size n goes to infinity. The reason is pretty simple. The reason we know, because the efficiency, mainly, we can see that better when the problem size is large. When the problems are relatively small, the overhead part will hide a lot of part of the efficiency. So we don't want to see, the overhead part distort the efficiency analysis. So that's why we want to look at the ratio when the problem size goes very large. All right. Yeah. Now let's do the ratio and take the limit. Let's try to find this limit. Okay. Yeah. How many cases do we have? If we look at this limit, how many cases do we have? Yeah. Here I give 4 cases. The limit equals 0. The limit equals non-zero constant c. Yeah. But for our particular situation, so remember the growth functions in our situation, each function represents running time complexity, right? Yeah. So the function, usually it's a positive function. So we consider the positive function. So this c should be a positive number. Positive number. Yeah. Okay. So then the third case, infinity. Yeah. Positive infinity. Yeah. And other. There is a other case. None of the 3, there is that other case. Yeah. So we will look at the other case a little more. Yeah. So let's look at these 4 cases one by one. Yeah. All right. Case 1. Case 1, what does that mean? When n is very large, the ratio f of n over g of n close to 0 approaches to 0. What's that really mean, right? Yeah. So here, direct meaning of that, order of growth of f of n less than order of growth of g of n. Order of growth. Here we have this concept, order of growth. We know when the problem size larger and larger, the running time complexity should be growth, right? But when that function grows, there is some order, right? Sometimes it grows faster, sometimes slower. And how fast, how slow, we may like to use a concept to describe it, order of growth. So this is a very abstract description, order of growth. Yeah. But here, to give you a little idea, I like to use some relatively simple functions so you can see the order of growth. Yeah. We know one function is just n. Okay? Yeah. Only n. You can feel about it, how fast it grows. Another function n squared, how fast it grows. Another function n cubed, how fast it grows. Right? Order of growth. There is some order of growth associated with 2n. There is some order of growth associated with n squared. There is some order of growth associated with n cubed. Right? Yeah. If you look at that, then we can compare order of growth like this. Okay? Yeah, the limit equal to 0. So we know the numerator function, order of growth of the numerator function is smaller than the order of growth of the denominator function. All right, so that's the case 1. Yeah. Case 2, C, non-zero positive constant C, we say those functions, they have the same order of growth. Because the difference is only about a positive constant. The positive constant, based on our previous video, when we do the ratio, remember, when we do that ratio, f of 2n over f of n, that ratio is gone. We cancel out when we do the ratio like this. Okay? That ratio, that positive constant is gone. Okay? So then these two functions have the same order of growth. Okay? So if you compare this, right? Yeah. Okay? Yeah. Limit, yeah. Especially we compare the limit, right? When n goes to infinity, right? Yeah. So now you can understand why that C is different, but we still treat these two functions have the same order of growth. Yeah. Because we know that constant multiple does not make big difference. No. It makes small difference, right? Small difference, but not big difference. Sometimes we can ignore, sometimes we cannot. So that's that constant. Yeah. All right. Same order of growth, case number 2. Case number 3, so you can imagine the opposite way, the order of growth of the numerator function is greater than the order of growth of the denominator function. Yeah, so that's straightforward. Okay, yeah, all right. Number 4, then we may feel a little harder to understand what is the situation for that other case. There is a important situation. The limit does not exist. That could happen, right? The limit does not exist. Okay, yeah. Let me give you a simple example. Yeah. Some students may not see how can it be possible the limit does not exist, right? Someone may ask a question like this. Yeah. All right, so here, let me give you a simple example. Okay. The numerator function, 2 plus minus 1 to the nth power times n squared plus 1. All right, so that's the numerator function. Denominator function, 2 minus 1 to the nth power times n squared minus 1 function. Can you see the limit does not exist? Can you see that? The limit does not exist. Yeah, because think about when n equals even and odd, right? Because these two, plus minus, the difference is very small. They are pretty much canceled, all right? Yeah, because for that situation, they're pretty much canceled. Yeah, because if another way to see that, if we divide it by n squared both sides, this becomes 1 over n squared. Here it becomes 1 minus n squared, right? When n goes to infinity, so this term goes to infinity, this term goes to infinity, okay? Yeah, so this term goes to 1, this term goes to 1, right? So this part does not change much, okay? Yeah, so when we consider the limit, we can ignore that part, all right? But now the remaining, this part, okay? Look at when n equals even, what is the ratio? N equals even, yeah, 2 plus 1, 2 minus 1, 3, right? When n equals odd, 2 minus 1, 2 plus 1, right? 1/3. So you can see that if we look at those numbers, 3, 1/3, fluctuation, up, down, fluctuation, then there is no limit. Okay? No limit. You cannot say the limit is 3. You cannot say the limit is 1/3. Limit does not exist. So you can see that special case we need to consider. Yeah. So here we take that out. Yeah. So we consider our case number 4, limit does not exist. Yeah. But here you can see if the limit does not exist, can we still compare two growth functions? Right? The limit method does not work, right? Can we still compare the two growth functions? We can still compare. Yeah. That only tells us the limit way is limited. Limit way is limited. It tells us that. But we can use non-limit way, right? We try to find a new method to give us solution for case 4. Yeah. So next, we need to look at that method. Yeah. Objective of our next part, even if the limit whole thing does not exist, we can still compare two growth functions in a new method. So let's look at that new method. Yeah. But before we go that, remember, so this part we need to learn the asymptotic notations. Yeah. Before we go to that part, so let me give you some reason why we need to introduce new notations, asymptotic notations. Yeah. So look at this part, case 1, case 2, case 3. We compare order of growth of functions. Yeah. So greater than, equal, less than, right? Yeah. That kind of relationships. We need to write many words, right? We need to write many words. That's not efficient. We want to use a compact way to represent the same meaning. Yeah. So we want to use symbols to represent the same meaning here. Compact symbols to represent. Yeah. So we use asymptotic notations to do that. For the first case, we introduce the little o notation. When we say order of growth of f of n less than order of growth of g of n, we just write f of n function belongs to little o, okay? Little o of g function. Yeah. What's the meaning of that? So here, this is our first asymptotic notation. This represents a set of function set, okay? A function set. Yeah. So we put them together, so we get a set of functions. What are those functions can be placed in this set? Okay. All right. Those functions, if you take limit with g of function, yeah, you do that ratio, you take the limit, you get 0, then you put in that set. That's the meaning. Okay? Yeah. With that, we have a compact representation. So this is compact representation. Okay? Compact. So we don't need to write, many words like this, right? We just write this formula. F of n belongs to a set of functions. That set we call little o of g of n. Okay, that's simple. The abstract representation of a special meaning. Yeah. All right. Similarly, the case 2, they have the same order of growth. We use this big theta notation. Yeah. But this notation, later we will expand a little more. Why? Why this one we need to expand more? Yeah. Although here we use the limit equal to c, but there is a situation, there is no limit. Okay? F of n over g of n, there is no limit, but f of n still belongs to this function set. So that case we need to include. Yeah, so that's why we need to expand this notation to cover more cases. So that's case 2. Yeah. Case 3, we introduce another notation, omega, little omega. Yeah. In this case, the limit, infinity. Yeah. In that situation, we use this little omega notation to represent. Yeah. All right. Next, then we try to look at some more cases. Yeah. And we do not use the limit method to do it. Yeah. What's the new method we use? Yeah. So let's look at the slide. Yeah. We know here the situation. This is the situation we have so far. Okay. Yeah. Yeah. The solution is using upper bounds and lower bounds. When the limit method does not work, we can use upper bounds and lower bounds to replace the limit method. Okay. So what's the upper bound, lower bound? Yeah, you will see the detail. Okay. Yeah. How do we do it? Yeah. Let's look at the details. First, yeah, when we compare two growth functions, yeah, usually g of n is a simple function, relatively simple functions. Yeah, usually, yeah. It's not always. Yeah. Sometimes if you use complex functions, it's okay, but when we use relatively simple functions to do comparisons, we can see the result easily. Yeah. So that's why people like to use simple functions. Yeah. And f of n could be a complex function. Yeah. G of n is a known simple function. F of n is a, harder, more complex function, but we want to know its growth function, the order of growth. Yeah. All right. And all right. So here, when we talk about upper bounds, lower bounds, what do you really mean, those upper bounds, lower bounds, right? Yeah. When you see the title, you may not get exact meaning. So here we need to get the exact meaning of upper bounds and the lower bounds. What's the meaning? Use some constant multiples of g to approximate f of n from upper bound side and the lower bound side. So that's the meaning of upper bound, lower bound. Okay? Yeah. So more specifically, we do this. Yeah. We can find two positive constants, C1, C2, such that C1, constant multiple of g of n, we can use it to bound above f of n, okay? Upper bound. Yeah. Another lower side, C2, constant multiple of g of n, bounded below f of n. Yeah. That's the main thing we need to do. If you can find this kind of relationship, then you can describe the relationship for order of growth between f of n and g of n. All right. Okay. And another observation, this method works no matter the limit exists or not. Okay. If the limit exists, this method still works. Okay? If you can find upper bound, lower bound, you can still make your conclusion. Okay. If the limit does not work, this method can still work. Yeah. Even better, right? Because limit method does not work. So you can only try this method. So even better, yeah. So now you can see, with this new method, then we can extend our first limit method to cover more cases. So now we are ready to describe rigorously for our asymptotic notations. Okay, all right, so let me describe one big O notation. Okay, so big O notation, big O. Okay, yeah, yeah. So big O. All right, so let me write. Okay, big O. So what's the meaning? So that is f of n belongs to big O of g of n. What's the meaning of that? Big O notation. All right. For a given function g of n, because we use it as the standard, we use other functions to compare with this standard function. So g of n. Yeah. The notation big O of g of n represents the set of function. Okay. Always set of function. Asymptotic notation always represents set of functions. Okay? F of n that satisfy the following condition. So what condition? There exists some positive constant c. One constant. Here we consider two constants. But for big O notation, we only consider one constant, one bound. One bound. Yeah. Not both. Yeah. Only upper bound. No lower bound. Okay? Yeah. And some non-negative integer n0 such that this inequality holds. F of n has an upper bound that is a c multiple of g function for all n less than or equal to n0. Yeah. That's the definition of BigO notation. Yeah. But you may, so because this definition is pretty abstract, so you may feel, what is this n0? What is the role of this n0? Yeah. To understand its role, if you recall, I gave you some description of algorithm efficiency before about the overhead part. When the problem size is relatively small, you need to pay a lot of cost to cover the overhead part. So basically do preparation, the overhead part. Okay? Yeah. This n0 corresponds to the overhead part. Yeah. So you want to skip that part. Okay? You don't want to look at the overhead part, right? So that's why this means you skip the overhead part, n greater or equal to n0. Yeah. Okay. But how large is the overhead part? There is no sure answer. Sometimes this n0 could be small, sometimes the n0 could be large, because you need to pay more cost to cover the overhead part, right? Yeah. But it has this property: as soon as you select that n0, then it must be fixed. That means it must be fixed. That means when you change this n number, the size number, you never change the value of n0. You only have one chance. You select it, then you must fix it. You do not change it frequently. Okay? The first time you have freedom to choose it. As soon as you choose it, fix it. All right? Yeah. So based on that arrangement, then you get a upper bound, constancy multiple of g function upper bound to control from the higher side of f function, then you get this BigO notation for the set of functions to describe f function. Yeah. All right. So that is the introduction part for our asymptotic notations. Now, our next video, so we want to try to understand a little more the meaning of asymptotic notations, but from graphs. Yeah. So we want to get some visual understanding on asymptotic notations. Yeah. All right. Yeah.